Hi. Before we start, I just want to get one thing out of the way, which is how to pronounce the name of the thing I'll be talking about. It seems there's a problem with it, and Hacker News notoriously has they're just trying to figure out, and there are all variations of pronunciation of this. Asciinema? No, not really. Asciinema? Yeah. Well, someone said I've always pronounced it Asciinema. Not really. So yeah, I pronounce it Asciinema because it's a combination of English ASCII and ancient Greek kinema, which means movement. Kind of smart name, and sometimes I wish I've chosen a different one, but here we go. 14 years later, it's too late. So about me, I'm a computer geek. I've been working with computers my whole life, and currently I work as an independent consultant. I specialize in Elixir and Rust development. I've been involved in open source for last 15 years, and I've created Asciinema, which I'll be talking about today. So what is Asciinema? It's a suite of tools for recording, replaying, and sharing terminal sessions. Soon it will be also for live streaming terminal sessions. The source code can be found on GitHub under Asciinema organization. There's a documentation page with comprehensive information about all types of things you want to do with it. And you can follow the project on Mastodon. The project is built out of 4 components. There's the CLI, which is the thing that you run in your terminal, and that's the thing that actually records a terminal, either to a file or streams it somewhere. We'll see where in a moment. So the player is the second component of the project. It's a web player running in a browser, which looks like a typical video player, but it doesn't play video files. It plays light terminal session recordings in ASCII cast file format. Nice thing about the player is that you can actually pause the playback and select the text and copy and paste it. You can't do that with a regular video. Another component is the server. The server we'll be talking about today quite a lot, and the server provides a hosting platform for the recordings and also acts as a live streaming relay. And all of the 3 components, the first 3, they embed a library I built called AVT, Asciinema Virtual Terminal, which implements sort of a terminal emulator, but a headless one without any GUI, which can be programmatically used to query the virtual state of the terminal window and do some other cool things with it. So how it all works? It all starts with the CLI, where when you run it, it uses a thing called PTY, pseudo terminal. This is a capability of Unix systems which allows a program to become kind of like a man in the middle between a shell and a terminal window, intercepting all the output that the program produces. So this is what Asciinema terminal recorder uses, and this is the PTY is used in other things you use daily, like SSH, tmax, and things like that. There's a more like in-depth information about how it works on the documentation side. So the CLI allows you to record, replay also inside the terminal, upload a recorded session to the server. There's one I maintain at asciinema.org, which is like the primary Asciinema server instance, but you can self-host it as well. And you can also run Asciinema stream to live stream in terminal. Initially, the recorder was a simple Python script, like 14 years ago. It was growing, and then I was liking working with. I work less with Python these days, so I just rewrote it in Rust. The player, as I mentioned, kind of looks like a video player, but it's built from scratch with JS. Embeds AVT library, so it embeds its own virtual terminal emulator to basically like get a view of what's happening in terminal and then render it using typical browser capabilities like span elements with different classes and styling. And the server. So the server is the thing that we'll be mostly focusing on from now on. The server also uses the AVT library to get some. We'll see in a moment. But yeah, also embeds the AVT library. Again, the library is written in Rust, so the Elixir application uses Rustler library to bridge those two, basically turning the Rust into an if that Elixir code invokes. The server, and basically the whole project was started 14 years ago. It's quite a lot of time. And it was, back then, a Ruby on Rails application. So it was fine, but then 7 years ago, I did this, and it became a Phoenix application, Elixir application, and it was a really good decision because it enabled a lot of cool things that we will see in a moment. So the server provides basic hosting features like a typical video hosting site would provide. So a page with a recording, some index pages for exploring what people uploaded. Also like a profile page where you can see my list of my recordings and that I currently live stream. That's a screenshot. I currently don't stream. Okay, let's talk about tools. So there's quite a bunch of libraries that Asciinema server uses under the hood. Most of those are actually used in this live streaming feature. That's almost there. Like it's ready, it's working, but kind of not fully announced yet. But those things we'll look into, and those things are in use by the live streaming feature. So the CLI can stream your terminal in two modes. One mode is the local server mode, which starts a built-in HTTP server with a basic page with an embedded player. You can open it and you can watch it. If you're on a local network, that works, and the stream doesn't go through any third-party server or outside of your network. There's a second mode, relay mode, where Asciinema server is used to forward to accept the stream from the command line, from the CLI, and to forward this to all the viewers that have the player connected to the stream in their browsers. And we'll look into that now. So all of the things that we saw, the list of tools there, most of them actually rely on a properly formed Erlang cluster, like Phoenix PubSub, Phoenix Tracker, Horde, etc., etc. So the server uses libcluster to automatically connect all the server nodes together in a cluster, and then it all just works like magic. So here's a ASCII diagram of the streaming feature. So at the top we have the CLI, which runs in your terminal. It opens the WebSocket connection to a producer socket on the server. The producer socket forwards the incoming stream to the stream server. Stream server is a gen server we'll see in a moment, and it just is a kind of like a manager of the stream. The stream server forwards the stream to all the consumer sockets. Every viewer connects from a browser, from the bottom looking, opens the WebSocket connection as well to a different endpoint, and gets the stream forwarded from the stream server through consumer socket. So Lightstream Producer, it's handles the WebSocket connection of the producer, so the CLI that streams. It receives the session stream, it parses it, forwards this to, as I mentioned, forwards to the stream server. Also performs things like authorization, bandwidth control, supports several encodings, and does a few other things. So first thing, it implements Cowboy WebSocket behavior. So Cowboy web server, which Phoenix uses by default, has this ability to implement your own WebSocket connection handler, which runs as a process, and you just need to implement a behavior and configure routing. So you can't easily do that in the Phoenix router, but you can configure the endpoint, specifically the dispatch configuration, to inject your own WebSocket handling modules. So there are two endpoints for the lowercase s, ws/s, and ws/uppercase s. Those are two socket handlers for the producer and for all the consumers, aka viewers, and it delegates everything else to the standard Phoenix endpoint. Implementation is quite simple. You just need to upgrade the HTTP connection because Cowboy treats that as a way for you to extract some information from the incoming HTTP request. So it passes the request here. You can, from the bindings, which are like parameters, extract the information, and then it will upgrade the connection to the WebSocket, and then it will start accepting the messages. So every message sent by the CLI will be handled here, and the producer socket will supports multiple, as I mentioned, encodings. So it can accept raw binary. It can accept Asciinema live stream binary encoding, and also text, which would be just a JSON encoded events. And this producer socket also does this thing where, like, if it terminates and the reason is remote, which means that the it was cleanly closed by the CLI. So that means that someone who was streaming just finished the session, just ended it. Then we also stopped the live stream server, the gen server we'll see in a moment, because it doesn't need to run anymore. Yes, so the next thing, dynamic supervisor. So every time a new producer connects, we need to spawn this new stream server. And I use dynamic supervisor here because upfront I don't want to run all the processes for all the inactive streams, right? So this uses dynamic supervisor, and mostly starting the servers through this ensure child function, which ensures that it runs. It tries to start it. If it gets an error that it's already running, fine. I just want to know it's there. Bandwidth control. Another thing that producer socket does is something that initially I thought, or I never thought of it, but the thing is that the terminal streams are very unlike regular video streams. They don't have a fixed bit rate. So video stream has like 1 megabit per second or something, and it's fixed one. Here, the amount of data that arrives from the producer highly depends on what's going on in the terminal, because it's all event-based. There's no like capturing the terminal window at a fixed frame rate. There's everything is event-based. So if I just go for a coffee and during my stream, no messages are being sent. But if I run some high frame rate animation, there will be a lot of data being sent. So to prevent abuse and resource exhaustion on the server, I implemented a bandwidth control using a token bucket algorithm. It's a really cool algorithm and very simple, actually, used in telecommunications, which basically let's look at how it works. So then for every producer who connects to the server, there's a bucket of tokens, and 10,000 tokens are added to the bucket every 100 milliseconds. So there's at the rate of 1 megabyte per second, and 1 token is 1 byte here. The bucket can hold at most 60 million tokens, so 60 megabytes. If a token arrives when the bucket is full, it is discarded, so there's like a maximum amount of tokens you can have. And when a packet arrives, someone printed something in the terminal, and so there was like a text, hello world, that would be like 10, 11 characters, let's say. So we see if there's a budget for that. If there is, then we just continue, just take those 11 tokens from the bucket and forward the data to the stream server, which will forward that to all the viewers. But if there are fewer than n tokens, then we just close the connection because someone just bombarded us with lots of data. So that's one thing that also producer socket does. So now the live stream server, that's the one that started by dynamic supervisor, and this guy just manages the stream, does a bit of bookkeeping, maintains some statistics, and publishes all the stream events using Phoenix PubSub. So the consumer sockets can subscribe to it and forward it through the WebSocket to the browsers. Right. So since there can be just one, there should be just one stream server in the whole cluster, we need to make sure that there's only one running. Doesn't matter on which node, but we need to be able to locate it easily. So I used Horde registry library, which allows process registration through its own implementation, a distributed one, and using the name option here and using the via tuple function, which tells OTP to register the name of the process using Horde registry. And then all the interaction then goes through also using the via tuple, because we need to first locate where is the process there, on which node, and how to call it. Right. So also the stream server also maintains a stream state, basically having a picture of what's inside the terminal, like having a virtual view of the window, what state is the terminal in, where's the cursor, what is the current selected background and foreground color, etc. So the AVT library is also integrated here, as mentioned. Yes, so right. So the server also sends updates using Phoenix PubSub, as mentioned, to the consumers, and using just a update struct with some extra information. When the producer socket calls the stream server with a feed message, the data is being fed into this AVT, into this virtual terminal emulator in the state. We keep the reference to it in the state, but it's a reference to a Rust data structure thanks to the Rustler library. And it forwards the same thing to publishes, which gets forwarded. So basically everyone who's currently online will just rely on this being published and being sent in real time. But the purpose of maintaining that state is that if someone connects later, and I'm currently away for a moment, nothing happens. So we need to send the current state of the terminal to the viewer, because in the JS player also the virtual terminal emulator runs. So in all parts of the stack, it's there. Right. Publishing topic, yeah. Phoenix track. Okay. Viewer tracking. So I wanted to implement how many, like this little thing that says like 5 people watching or 5,000 people watching next to the stream. So I first look at Phoenix presence, which is kind of more popular sibling of this guy. But Phoenix Tracker is actually simpler and more suitable for this. So I use this module. Implementation is rather straightforward. Also use here updates track, which is being published when the viewer count changes. So different parts of the stack, different processes can subscribe to that. It exposes track and untrack functions, which the consumer sockets call. So whenever, we'll see that in a moment actually. You can always get a current count of the viewers from it, and you can subscribe for updates to the view count changes. Yeah, and here's a actual callback implementation of Phoenix Tracker. The Phoenix Tracker requires this one, and inside of it I just reshuffle it and publish it through PubSub. And one more responsibility of the stream server is keeping database schema up to date, like periodically taking a snapshot of a stream, saving it in a database, and then those snapshots get displayed as like small cards in a view on your profile, for example, when you stream. So the stream server uses the subscribe function, right? So it gets let's see, yeah. So it gets those messages, viewer tracker update messages, and stores it in its own state and updates the database on its own schedule. So it's not like overwhelming the DB if those things happen quickly. And livestream consumer. So this is the module that handles the process connected to the WebSocket of the consumer, the viewers. It also implements the Cowboy WebSocket behavior, just as the producer socket. This one uses livestream server for subscribing for stream events, so it can forward them to the browser. Uses also viewer tracker to subscribe, to register them, to register itself as a viewer, basically. So every consumer socket is counted as a viewer, basically here. So after getting a stream from the database, we subscribe to the feed, to different status messages, and we tell viewer tracker to track us. So the process, the consumer socket process, and we send them the initial header message of the stream. And so after subscribing, we get those fans. We can then forward the reply here. Tells a Cowboy WebSocket to send this message over the WebSocket to the front end. Yes, and this is important as well. So whenever a viewer WebSocket disconnects, we get this terminate callback called, and then we untrack ourselves from as a viewer, so we are not counted anymore. Right. And here's a one nice thing about Elixir and Airline, that those messages that are sent to the front end are binary messages, and the header message is quite simple. We have a feed message, so that's like basically that what got it includes what was printed to a terminal and it's forwarded there. So the structure of a message here is like built from those little elements. I like to call this like reverse pattern matching, which is because it looks like a bit like pattern matching of binaries, but you're kind of constructing instead of deconstructing. And this is super easy, like in Elixir. Okay, live views. So other than handling the viewer, so the consumer socket basically talks WebSocket, and it sends the stream to the JS player, which doesn't use live view or anything. It just connects to the WebSocket endpoint and gets those messages and does it on its own. But there are a few live views that I use here. So here's my profile page. Again, the first card here is a preview card of my live stream. It's pretty much the same as the ones below, which are for the recordings that I uploaded earlier. But this one is live. It's semi-live. It's updated once every 10 seconds, but it updates, and it was kind of super easy to do with live view. I already had this card functional component, which is a stateless component, just renders a thing given its attributes, and I wrapped it in a live view just by putting it inside the render. and subscribing to the stream metadata changes. So whenever metadata, such as a snapshot, preview of the terminal window changes, this live view gets an update, assigns the updated, the new data to the socket, and then live view re-renders that. So this was just super easy to do here. Also, another live view, this small status bar displays like how long the stream is running for, how many viewers. So this was also super easy to do with live view here. Again, subscribing to some events from the stream server, and also subscribing for viewer count changes thanks to viewer tracker subscribe here. So that also was just a matter of implementing those callbacks, assigning few pieces of data to the socket, and it was live. Yeah, I guess that's it. That's all I have. Thank you very much.